Okay, given the background of what we have done so far, right, I am going to be talking about the neural machine translation in this particular session. So, earlier we had seen how sentences can be translated from one language to the other using the statistical models, right. Especially we saw models in terms of IBM models. We actually spoke about two models. One is IBM model 1, the second one is IBM model 2, and then both had given very interesting perspective with respect to translation. Model 2 really provided us in terms of alignments, right. So, how do you really align words from one foreign sentence to the native sentence that you have in mind, right. So, it provides some alignment models, and then we used a noisy channel model to really break that into two distributions. One is the language model, second one is the translation model. In the translation model, we actually added more nuances in both model 1 and 2. Model 3, 4 and 5 actually added more nuances to that. And then later we also spoke about the phrase based models, where we try to align phrases and not just words. The reason for the better translation is we started attaching the context. We are not just looking at only one word translation. We are now looking at context. So, that context really provided some meaningful translations. Okay. So, until 2014 many systems used phrase based models, and then when they evaluate their system, they used a Blue, Meteor, NIST based model, WR, WER, all those evaluation metrics to find out how close their translation is with the human translation. Okay. So, now we jump into the next phase of translation, where neural machines are coming into play, right. Why do you think neural machines would do a better job? You remember again in the case of word embedding model, given 3 inputs or 4 inputs in the SKIBO model, right, neural net is able to really relate them together because the context is available. So, it is able to really relate one single word with multiple words in the output, or multiple words in the input to one single word in the output layer. So, it is all about identifying the patterns in those, and then how do we really align those patterns, so that when a new input is given which is close to the pattern that it has found, it reasonably provides a good output. So, can we extend the same thing to the neural machine translation? Remember, even in the RNN model, we provided a sequence of input, right. The sequence of input we provided, and then there is an outcome that comes out of that, which is nothing but the encoding of that sequence, right. For example, I can encode a variable length sentence into one vector as the outcome. I can use the same sequence to train the network to recognize the words that are coming as next, or I can simply put it, I can call it as a language model. So, it helps you in terms of training a language model, or you can also use the same sequence mechanism to find the spellings. Supposing if you had given a large corpus and then make the system learn the large corpus with respect to English words, and in that you are only giving one character at a time. So, when you provide the characters in characters to the RNN as a sequence of letters or sequence of events, it learned the spellings as well based on the corpus that you have provided. So, now we want to extend this further. Again, you should understand that in the progression that we have been seeing so far, we started with understanding the frequency of words. I am starting from the beginning. Okay. We have that term frequency and then IDF that we have inverse document frequency, and then we combine them, and then later we have used an LSA model to find out the association of the words that are coming in the term document matrix, and then later we moved from the words alone into the language elements of that. We try to create a language model by using the corpus or the statistics that is available as part of the corpus, right. And then from the words and then the group of words, we started to understand the context by giving more input words to the models, either a trigram language model, and when you go to the neural net side of it, you had given CBOW, where you give more words and then one word is obtained as the output, or in the skipgram you give one word and then it identifies the context word surrounding that and so on. So, we are able to go from the word to some extent to identify the context of the words, and also to some extent to identify the meaning of those words that occur in the context, right. So, next we extended that in the RNN model, where we were able to encode a sentence, correct. So, the next stage is, after you encoded a sentence, is it possible for me to use the encoded sentence to do the translation. So, this is the progression that we have been making, correct. The translation is the next level of intelligence in the Bloom's taxonomy. I am not sure whether you still remember the Bloom's taxonomy part that we studied earlier, where we started with the knowledge recall and then application analysis, and then later we said the creation part of that, right. So, slowly and steadily we are trying to provide some intelligence to the machine, so that it moves up in the pyramid part of the Bloom's taxonomy as well. So, when you look at the translation part, it is considered to be an human intelligence task, correct. So, we want to see whether the machine is able to really create something, evaluate that creation, and then say that, okay, what I have created is good enough for you to take it forward. So, that is where the higher levels of intelligence coming into play, correct. So, we want to see whether the translation models are really getting into the higher levels of intelligence that is actually used to really figure out how the students are learning the subjects. Okay, I am also sure that you know that many of the question papers that you had seen so far in the exams have followed some patterns of that. There will be some recall, right. So, you just have to recall the answer. In some cases you have to use your knowledge and some ideas and then apply it to solve certain problems, and then you are asked to create or synthesize something. That is where the creation starts, right. And then finally you innovate a few things, for example the breezy writing part in English. You are really doing some innovative writing there after looking at the phrases or the paragraphs given to you. So, the progression is very interesting even in the case of the natural language processing, especially when you start with the data model. I am sure you have noticed that I have not gone into the syntax elements of the language. We have been only talking about the data part of that all the time, and we moved from the probability to the neural elements because of a lot of interesting pattern matching that is taking place in the neural net world. So, coming back to this part of neural translation, we are going to be using neural networks to really find out whether it can do a good job in the translation or not. So, it all started in 2014. We are not very far from the current world of translation. Okay. All right. So, given the introduction, let me jump in. I think I gave some ideas about this. So, we are going to be using two sequences. One is the native language sequence, and then there is a translated sequence on the other side. So, you can, in this case, it can be interchanged. Okay. So, I can give English as one sentence, and we have a box which we call as the neural machine translation black box, and it will output the foreign sentence, or you feed in the foreign sentence, it outputs the English sentence or any other language sentence. Okay. So, in this case there are going to be two sequences. One is the English sequence, we will use the convention, and second one is the foreign sequence. And we are going to be using the same RNN model for the translation. We know that RNN is meant for sequence modeling, correct, or sequence learning. So, in this case we are going to be feeding two sequences at different times, okay. And then when this is fed, okay, we expect in the different time slice an output of a different language. Okay. So, in this case we are not going to be doing any complex mechanism that we had done in the phrase based model or in the standard statistical machine translation models. We are going to build a very simple single large neural network that reads one sentence and outputs the correct translation. Okay. So, this is the idea. Okay, let us jump into the next zooming in part, right. So, we have seen from the very top level what neural machine translation is. Given a sentence in foreign language, it is going to output an English sentence. Okay. So, the next part is, okay, we are going to have two things here. One is an encoder, another one is a decoder. Okay. It is very similar to what we had seen in the noisy channel also. There is an encoder and a decoder. So, in this case we do not need to really compare that there. The encoder is an RNN, or decoder also is an RNN, because both take a sequence of sentences, right. Okay. So, we have a target source sentence, a target sentence. Advantage of this again is you can give variable sentences of variable length. Okay. So, that is the advantage, and then again the sentence length when you have in the source, right, need not be same as what is coming out in the decoder as well. It could be smaller, shorter, maybe the encoder will have a 5-word sentence, the decoder may provide you about 7-word or 8-word or 3-word sentence and so on. It depends on how we provide these sentence pairs during the training. Okay. And it uses a fraction of memory needed. You remember when we spoke about the phrase based model, and then I also showed a table the size of the phrases that are required, correct. It runs a few GBs and it is not really very efficient in terms of using the machine. So, RNNs use very small memory footprint. Okay. We have to say that the model is not going to be doing very well when the sentence is long. Why? It is the same reason that we mentioned earlier with respect to vanishing gradients, right. So, when the sentence is long, it is not able to remember everything very clearly. Okay. So, the performance of this system would degrade. So, okay. So, it is not that we have cracked the entire translation problem, we are making progress and doing better than what we have done earlier. So, that is what I should tell you at this point in time. It is not that every translation system in the neural net side provides you 100% translation. It is reasonably better than what we had seen in the phrase based models of SMT. Okay. It is still in progress, the research is still in progress, we still have not succeeded in every area of translation, but these are the fundamental elements that are now taking the translations from where we are. Actually, the translation was going in the speed, and then suddenly it moved up from 2014. So, this speed with respect to the research that is going on in the machine translation world is fascinating, and lot of excellent results are coming out as well in this. Okay. Okay. All right. So, as I mentioned earlier, there is going to be two RNN that we would use, one for encoding, another one for decoding. Okay. So, let me go back to the previous slide. I think I have not spoken about this part. So, what we have here is there is an encoder, okay, that encodes the source sentence and then provides you this, I think you know, right. It gives you a vector. So, we call it as a context vector. So, it encodes all these words in terms of a vector, in terms of some numbers, and then this is fed into the decoder, and then decoder uses this input along with its initial state and then start decoding word by word. Okay. And the training happens in this fashion. Let me erase some of these. So, earlier in the case of RNN, when you have right, when you start feeding the sentences, it happened within this encoder part, right, in one single box. So, now the training has to happen because we have added the decoder part and the entire chain has to be trained. That means, we are going to be having a lot of parameters to update, all right, during the training process. Again, you can use the same back propagation through time to do the job. All right. So, remember, this is a very simple set of several matrix manipulations and vector manipulations, all right, nothing more, nothing less. This encoder RNN could be your LSTM, GRU or what not. The cell could change as well. There are so many combinations that you can bring in because of that. All right, continuing on this part, encoder maps the variable length sentence into a fixed length vector. As I mentioned that the output is going to be a fixed sized vector. Decoder translates the vector representation back to a variable length target sequence. Again, when the decoder receives the context vector value, it inputs that as part of the first value along with the hidden values that it has, and then it starts providing the first word. For example, this is the starting of this sentence and I have the RNN. After softmax, it provides some value, right, and let us say the is the or the is the first word that needs to be output from the decoder. Okay, encoder has a French sentence. Let us say la is the first word, and then after encoding all the words, we have a context vector, and then this context vector is fed in here as part of this, and then since this sentence is known to us, okay, let us say the book is on the table, is this, and we know that this is the book, should be output, and then this is going to be outputting is and so on. You know how the progression goes, right. Sorry about the messy stuff, but I think you understand this. So, from the encoder, after incorporating the context vector, the output of the first decoder should be the, correct. So, it knows that the has to be the first one, and then it outputs that and then makes the changes. You can have a small a back propagation in this to adjust this, or you can do it till the end. So, there are mechanisms, as I mentioned, you can have several learning mechanisms combined into this as well. Okay. These two networks are trained jointly. So, as I mentioned, so it goes from the decoder to encoder and then encoder to decoder, and the process goes on until the network stabilizes, right. So, what essentially that means, it is again the same, right, the conditional probability that we talk about. Given the English sentence, supposing if you are inputting into the encoder English sentence, we are expecting f as the outcome. So, the conditional probability is what we are estimating here. Okay. Given E, we are providing the probability of this particular sentence in French, right. So, that is what we are trying to estimate at the end of this. So, it learns a continuous space representation of phrase that preserves both semantic and syntactic structure. Since we are inputting the sequence, right, so we are not losing anything here. We are inputting sequences of words. So, we are not providing only a bigram or trigram, we are providing the entire sequence. So, that means the entire semantics also is passed along with this, and the network learns in both cases for both in the encoder box as well as on the decoder box. Okay, so, it learns continuously those phrases in the continuous space.